Okay. So we were doing chapter 7 review, and we will do problem 2. What is the mass in grams of 4.48 liters of O2 at STP? And as I said, O2 is the diatomic molecule made of 2 atoms of oxygen, and that makes the molecule of oxygen, that we call it the same way. And it's the oxygen you breathe that comes from the air. And at STP, so if you have started to learn chapter 7 here, you know that STP means, and let me write it here. STP means standard temperature and pressure. It's an acronym to say this more quickly, because you know, gases can be so different depending on the temperature and the pressure, and so to be able to compare them more easily, we have a set of standard temperature and pressure values, which are 0 degrees Celsius for temperature, 0 degrees Celsius or 273 Kelvin, and the pressure is 1 atmosphere or 760 millimeters of mercury. You know, there's many units. So that's what this means. But you know, sometimes you only need to know that it's at STP, and you don't really use those two values of temperature and pressure. And here that might be the case, because there is what we call the molar volume. The molar volume is telling you that at, so I will write it, 1 mole of any gas, sorry, change that. So let me make this blue so we see what I'm doing. 1 mole of any gas at STP is equal to 22.4 liters. This is called the molar volume, and it's a value that is very convenient because it is true for any gas, and 1 mole of any gas at STP will occupy that volume of 22.4 liters. And so knowing that it's at STP tells you that you can use this fact, the fact that 1 mole of any gas at STP is equal to 22.4 liters. And so that can be convenient here, right? Because we have, so the given here is 4.48 liters of O2, oxygen, right? And it is asking, we want grams, so mass in grams. So what is the mass in grams of, you know, 4.48 liters of oxygen? So we cannot go from liters to mass, right? Obviously, there is no relationship between grams and liters. However, we know we have this relationship between liters and moles and grams. We know we have the molar mass for that, right? Whenever you have to change moles to grams or grams to moles, you can use the molar mass. So we will then use the molar mass of O2. So molar mass of O2, because that's the gas in question here. And so for this, you take your periodic table, take the mass of 1 atom of oxygen, so 16.00 mass of 1 mole of atoms, so 16.00 times 2, and it's 32.00 grams per mole of O2, right? Let me put this here so that we know we can use those two equalities. And so let's write the roadmap for that. So we start with liters of O2, no, O2. O2, oops, 2. And we will change that to, make me 2. We will change that to moles of O2. And then once for this we will use the fact that 1 mole of any gas occupies 22.4 liters. So that will allow us to change liters of oxygen to moles of oxygen. And then from moles of oxygen, we can find grams of oxygen by using the molar mass of oxygen. So I think we are ready to do the calculation. And so always start your calculations with the given amount. So 4.48 liters of oxygen. That's the given amount. Multiply by the conversion factor, and we will have 2. So times another conversion factor equal. So so the first conversion factor is supposed to change the liters of oxygen to moles of oxygen. And so for this, you will use this equality. 1 mole of any gas at STP occupies 22.4 liters. We have liters to start with, so we will want to put liters on the bottom. So the 22.4 liters will go on the bottom. And then on top, it's going to be 1 mole of O2, right? We need to adapt here. It's 1 mole of O2 occupies this volume because we are at STP. So that changes the liters into moles of oxygen. And then in the next step, we want to change moles of oxygen to grams. And we will want to use the fact that 1 mole of O2 is 32 grams of O2. So, but the next conversion factor here in the denominator should have moles of oxygen so that we can cancel moles of oxygen. So 1 mole of O2 on the bottom and 32.00 grams of O2 on top. And so here we see that liters of O2 cancel, moles of O2 cancel, and we're left with grams of O2. So we know it's correct because that's the desired unit, mass in grams. So in the calculator, you do 4.48. Let's multiply all numerators together. So here times 1 and times 32.00 divided by 22.4. And it's 6.4. So we need to pay attention to sig figs. The molar mass has 4 sig figs. The 1 mole are exact. They don't limit. 22.4 has 3 sig figs. So from 4 to 3. And the given amount also has 3 sig figs. So the least amount of sig figs is 3. So here we need to add a 0 to show 3 sig figs. Otherwise we would remove precision to the the measurement. So you have to add a 0 to make it 3 sig figs. And so that would be the mass of oxygen that is occupying about 4.5 liters of oxygen at STP. So 0 degrees Celsius and 1 atmosphere. Do you have questions on this one? So the molar volume is in your reference paper here. It's what is on the yeah, it may not look like that for that's the one I sent, but for others on the right side of the first page of the reference, you have things for chapter 7 here. The pressure units, the equalities between them, standard temperature and pressure, what it means, it's written here. And then the molar volume here, 1 mole of any gas at STP is 22.4 liters. That's an important statement here. Then the ideal gas law, P times V equals nRT. And the value for the R constant, depending on if you have a pressure in atmosphere or millimeters of mercury. And then Dalton's law of partial pressures. So all of this is for chapter 7, and it's on that first page of the reference. Should have shown that earlier, but okay. So that was the first problem. Maybe not the easiest to start with, but so let's do problem 3 now. What is the pressure in atmosphere of 1.50 moles of neon in a 5,000 milliliter steel container at a temperature of 125 degrees Celsius? So what is the pressure in atmosphere? So we are looking for P. So let's write this. What? P, capital P. Pressure is in capital in atmosphere. And what is given? So we have different things that are given, and that's typical when you are dealing with gases. So here it's a number of moles, right? So N, we have N equals 1.50 moles of neon. So this is a volume, right? You all see that it's a volume. So volume is 5,000 milliliters steel container. And then we have at a temperature of 125 degrees Celsius. So T is the temperature, 125 degrees Celsius. So it looks like, so can you tell me what gas law do you think we will use here? Is it Dalton's law and the law of partial pressures, or is it the molar volume like we just saw, like we just used here? Or is it the ideal gas law? Can you tell me which gas law we will use? We know N, we know V, we know T. We're looking for P. Yes, we will use the ideal gas law that says P times V equals nRT. You know, it's all multiplied together. So by using this, we have V, we have N, R is a constant we can find in the reference, and then T. Except that when you are using this, and let's go back to the reference here. So the ideal gas law here, P times V equals nRT, needs to use the ideal gas constant R, and the ideal gas constant R has you know, units, and you need to have your other variables following those units so that they can cancel. And so because of that ideal gas law constant, volume will have to be in liters, moles are in moles, temperature has to be in Kelvin always. And that's true for any kind of equation that uses the temperature. As I explained earlier, the temperature is a measure of the kinetic energy, the energy of movement of the substances. And to be really representing that, it cannot have negative values like you have in the Celsius scale and the Fahrenheit scale. So to really represent a movement, it has to be only positive, and so the kelvins are used in science because of that. And then we have the ideal gas law, ideal gas constant, sorry, for when pressure is in atmosphere or when pressure is in millimeters of mercury. And here we were looking for pressure in atmosphere. So we will use this value, the left one. that says 0.0821 liters times atmosphere per mole and per Kelvin. So let's use that and go back to here. So we will use the ideal gas law with R equals to 0.821 liters. So I'll write it like this: liters times atmosphere per mole and per Kelvin, right? That's how you can see it. So our volume is not in liters right now, it's in milliliters. So that means we need to do a conversion of the volume from milliliters to liters. And hopefully you are at ease with that. You know, so 5 milliliters, and I should do that in the equation here. So 5 milliliters, you multiply, and we will use the fact that 1,000 milliliters equals 1 liter. Or you could use the fact that 1 milliliter equals 0.001 liter. Either or, it's fine, they mean the same thing. I like to use the 1,000 milliliter equals a liter. So notice how I place the 1,000 milliliter on the bottom of the denominator, because on the bottom of the conversion factor, because we want to cancel milliliters, right? And then I have the 1 liter on top because I want to, you know, end with that unit. So I should end with liters because the milliliters cancel. And so it's 5,000 divided by 1,000, and that's 5. So you have to be careful here because there is a dot in the 5,000. The dot here tells you all these zeros are significant. So you need to show that it's 4 sig figs, right? Because this has 4 sig figs. So it's going to be for 5.000, so that it's 4 sig figs, right? So that's now the volume in liters. Temperature. Temperature needs to be in Kelvin, and it's right now it's in degrees Celsius. So again, let's change that. Oops, I wanted to copy first. These are easy to change into kelvins, because to get the kelvins, you take the Celsius plus 273, right? And that gives you the kelvins. And so 273 plus 125, it's a 398 Kelvin. So now we have our temperature in kelvins, our volume in liters, and the moles are correct in moles of neon. So then we are ready to calculate pressure. And here we have pressure times volumes. So we want to have pressure by itself. So if you divide both sides of this, so let's copy that. And so hopefully you're at ease to change these. But here, if you divide both sides by V, you will see that on that side, it's going to be equal to P. You know, the left side is equal to P. So P is equal to nRT over V. So we'll do that then. P equals, make it, so N is 1.50, oops, that should be inside. Hmm. 1.50 moles of neon times times R. R is 0.0821. So R needs a small unit here of liters times atmosphere, and it's over moles times Kelvin. That's the full unit of R. It's a complex unit, but it's necessary to cancel all the other units and have the one you're looking for only. Times temperature it's 398 Kelvin. And all of this is over V, and V is 5.000 liters. So unfortunately, I cannot show how the units cancel, but here you have moles in the numerator, and here it's per mole in the R unit. So these two cancel, moles and moles cancel. Same here with Kelvin, Kelvin in the numerator, and per Kelvin in the R unit. So Kelvins per Kelvin, they cancel. Liters here in the numerator of the R value. And here, liters for the volume is on the denominator, so they cancel. And we are left with just atmosphere. Atmosphere is not cancelled. So the unit of what we find is in atmosphere, and that's what we want. So in the calculator, you do 1.50. Let's multiply all numerators together. Times 0.0821 times 398 and divided by 5.000. The calculator answer is 9.8275. It's more than what we need, but let's look at the sig figs together. So we have 4 sig figs in the volume, 3 sig figs in the temperature, 3 in the R value, and 3 in the moles, right? The 0 here is significant. So the least number is 3 sig figs. So we will keep the 9, the 8, the 0. What comes after the 0 is a 2. We need to round down, which means, so we'll keep the 9.8 and then 0. And we keep the 0 as it is because what comes after is a 2. And so then you drop everything after that, atmosphere. And so that's the pressure of this 1.5 moles of neon in that 5-liter container at 125 degrees Celsius. Do you have questions on this? No? Yeah, hopefully I don't go too fast because time flies and I want to make sure we cover enough. So, okay, so then we can continue with problem 4. So what is the total pressure in atmosphere of a gas sample that contains helium at 285 millimeters of mercury and oxygen at 1.20 atmosphere? So total pressure of a gas sample that contains helium and oxygen. So that should ring a bell. What gas law do you think we will use here? We have a mixture of gases. It's made of helium and oxygen, and we want to find the total pressure of that gas mixture. And so we can go to here. So what do you think you will use from, the formulas available from chapter 7 and gases? Yeah, Dalton's law of partial pressure, right? Because we are looking for a total pressure, and the total pressure is made of the partial pressures of the gases that are in that mixture. So we will use that Dalton gas law that says P total, and so let me use the equation here. So P total, so I'll just write all that equals, P of, so here we have only two gases in that mixture. We have helium plus P of O2. O2. Okay. That's how you want to interpret that gas law. It says that the total pressure of a gas mixture is equal to the partial pressure of the gases that are in there. So partial pressure of helium, which means the pressure that helium occupies in that container, like if it was by itself. That's what really is a partial pressure. And then the partial pressure of oxygen. So pressure of oxygen if it was by itself in the container. And we are given those values, right? Helium at 285 millimeters of mercury and O2 at 120 atmosphere. However, they are not in the same units, right? You see atmosphere for O2 and millimeters of mercury for helium. So you cannot add things that are not in the same unit. And so you have to pay attention also to the fact that the total pressure is asked in atmosphere. So it has to be in atmosphere. So then let's look at P. P of H2, He, sorry, is equal to, is equal to 285 millimeters of mercury, right? Millimeters, Hg is the symbol for mercury. And so this is the one that we need to change because pressure of oxygen is in atmosphere, right? I could write that. Pressure oxygen equals 1.20 atmosphere. So it's already in atmosphere. So it's this one we need to change. So we need to change it to atmosphere because the question is asking for a total pressure in atmosphere. So let's change it. And from the reference here, you can see that 1 atmosphere is equal to 760 millimeters of mercury. Hopefully you can see that this equality also means that 1 atmosphere is 14.7 psi and 1 atmosphere is also 101,325 Pascal, but the pascals are also equal to the 14.7 psi, etc. You can rewrite this the way you need it. All of these values are equal together. But we will use the first equality that is written here, the fact that 1 atmosphere is 760 millimeters of mercury. And we want to change millimeters of mercury to atmosphere. So the 1 atmosphere will go on top. It's the desired unit. And the 760 millimeters of mercury will go on the bottom. Equals. So let's multiply this together. 285 divided by 760. There's no need to multiply. So, and that's exact. The calculator answer is just that, 0.375. It happens to be 3 sig figs, which is what you need because you have 3 sig figs in the pressure in millimeters of mercury. 760 with the dot here tells you it's 3 sig figs. And the 1 atmosphere is exact, right? When you have equalities and you have ones, those ones are exact. So then we are ready to use this again and calculate the total pressure. And so we take 0.375 atmosphere from helium plus 1.20 atmosphere from oxygen. You calculate that and it's 1.575 atmosphere. Okay, so when you're adding, the rule is to keep the least number of decimal places So here we have 3 decimal places in the pressure of helium. And in the oxygen one, we have only 2 decimal places. So we need to keep the least number, which is 2. So we keep the 5, the 7, and we need to run there. What comes after the 7 is 5. So we said we keep the 5, 7. What comes after the 7 is a 5. So you need to round your 7 into an 8. You round it up. And that's what will be the total pressure of your mixture. Okay, so hopefully, do you have questions on this? Or? So it's already 11. So let me